The aim of this lecture is to describe AM technologies for metallic materials and to summarize the added value provided by implementing AM in local production. After this lecture, you will be able to identify key industrial sectors for the application of metallic AM technologies. The AM of metal has taken a huge step forward in industrialization over the last few years and in this area is growing rapidly. Currently, various machines and processes are available in the market for producing metal parts. According to the major industries, the most common processes to build a metal components are laser powder bed fusion, LPBF, electron beam melting, EBM, laser engineering net shaping, LENS. In the laser powder bed fusion process, also known as selective laser melting, direct metal laser sintering or direct metal laser melting, metal powder is selectively melted by a focused laser. In LPBF process, the laser beam passes through a system of lenses and it is reflected by mirrors to control the laser beam spot movement on the building platform. Either a recoating blade or a roller uniformly spread a layer of fresh powder from the powder tank to the top of the building platform or on the previously melted layer. Then the powder is selectively melted, the platform moves downwards and the cycle is repeated until the build is finished. The process takes place inside a closed building chamber filled with an inert gas, like nitrogen or argon, to minimize the oxidation. The temperature of the building plate is controlled in order to limit residual stresses and part distortion during the production process. LPBF parts must be anchored onto platform through support structures, holding them in place. Once parts have been fabricated, the build platform and attached parts are removed from the loose powder. Then operators remove the support structures by hand and carry out any other post-processing. A wide spectrum of material can be processed in LPBF, including aluminum alloys, cobalt alloys, iron alloys, nickel alloys, and titanium alloys. The materials can undergo post-machining operations such as milling, CNC turning, thermal treatments, and aesthetic and protective surface treatments. The LPBF process is suitable for the fabrication of final metal parts as well as pre-series ready for testing. It is used across a wide number of industry sectors, including aerospace, automotive, defense, medical, and tooling and automation. In electron beam melting, metal powder is completely melted by an accelerated beam of electrons. Either a tungsten filament or a crystal creates a stream of electrons that is accelerated to approximately 1/2 of the speed of light. An electromagnetic coil system is used for obtaining the right shape and size of the beam and the proper position on the powder bed, providing extremely fast and accurate beam control. The entire process takes place inside a closed chamber under vacuum, ensuring that oxidation will not compromise highly reactive materials. During the melting process, helium is introduced to better control the process. The electron beam hits the powder bed to a high and optimal process temperature that gives low residual stresses, no need for heat treatments, and a fine microstructure. Different titanium alloys as well as cobalt chrome and inconel alloys are used primarily in EBM technique. Thanks to this technology, components can be created with materials difficult to melt through traditional techniques such as titanium aluminide, titanium niobium alloys, or other elements. The electron beam melting is currently employed with success in the aeronautic, aerospace, and racing field. Mostly, the biomedical sector benefits from this technology, and in particular, the human orthopedic and maxillofacial surgery. Laser engineering net shaping is a directed energy deposition process that uses an injected metal powder flow as feedstock. along with a laser energy source to melt and deposit the material on the top of a substrate. In a building chamber, a laser beam focuses on a point on the building platform, and at the same time, metal powder is injected to the point through a powder nozzle. The melted powder and the material beneath solidify quickly, thus forming a layer of material. After one layer is built, the laser head and powder nozzle move up, and the laser heating and powder injection process are repeated for the next layer. With the use of high-power laser, process controls and the complete environmental control, the lens process supports many high-performance metals, including titanium, stainless steel, and Inconel alloys, with the quality required for critical applications. Thanks to its multi-axis fabricating capabilities, lens is also used to selectively build up word or damaged part in an additive process. Additionally, the process can be used for manufacturing and hybrid manufacturing as well as functional prototyping. In conclusion, I briefly introduce you to the several different AM techniques to produce metal parts available on the market. The most common processes adopted by major industries are laser and electron beam powder bed fusion and lens. Hence, AM metal processes could be a viable manufacturing process to fabricate products with a high added value. Moreover, AM enables distributed production networks, and it also allows manufacturers entering new markets at a relatively low cost.